is addition property. So addition is commutative. Commutative means u plus v equals v plus u. So you are going to add u plus v two vectors, you will get the result, and you are going to interchange those two vectors v plus u, you will get the same results. So this is commutative for addition. And second one is associative property. So you are going to add, now associative property will have three vectors, there must be three vectors. So you are going to add those two vectors first and with another one, which will be exactly equal to, you are going to add the last two vectors on the previous one. The answer will be the same. So this is associative property for addition. And there exists a zero vector. So you have a vector and you are going to add 0, you will get the same vector. So 0 plus w will be equal to w plus 0, which is equal to the same vector as I said. So this is w. There exists an inverse vector. You have an inverse vector. So w for addition, the inverse will be minus w. So w plus minus w, which is equal to minus w plus w, which is equal to 0. Okay. So those four properties come under addition. Now we will go for scalar multiplication. For scalar multiplication, as I said, scalars can be real number or a complex number. So it can be a real number as well, complex number. So there are three properties exist for scalar multiplication. For scalar multiplication, you have a vector dot product with the combined vectors. So u plus v is a combined vector, u plus v. So that will be your w dot u plus w dot v. Sometimes you have two scalars here. There are no scalars here. There are two scalars. Okay, and you have an vector. So that can be written as au vector plus bu vector. Okay, so this is distributive property for multiplication. Associated with respect to the multiplication, you have a and b are scalars. It can be either real or a complex number. So a and b are scalars. U is a vector. This can be combined. You can write this as ab of u vector. For each element there exists a unitary element I such that u vector I is a unitary vector. Unitary vector multiplied by u, which is equal to u multiplied by I, will give you the same vector u. Okay. So similarly, null vector, zero vector multiplied by u, which is equal to u vector multiplied by dot with dot product 0, which is equal to 0. So this is for 0 and this is for your unitary vector, unitary element. So it has to satisfy some properties under addition, some properties under scalar multiplication. It has to fulfill. So as I said, vector space in which you have a set of vectors, set of numbers will be there, and they can be either real or complex values. Real space is 3-dimensional space, we know already. Linear vector space is n dimension 1. The dimension of a space vector is given as a maximum number of linearly independent vectors. For example, you have 3 dimension, you have 3 vectors I, j, k, x, y, z. So we have 3 vectors. Those 3 vectors, as I said just now, they are linearly independent vectors. You count all the 3, that will be 3. So it means that 3 dimension. So 3 dimension means the maximum number of linearly independent vectors. Is it okay? The space which consists of maximum number of independent vectors are nothing but dimension. For example, 3 dimension, 3 linearly independent vectors. 4 dimension, 4 linearly independent vectors. 6 dimension, 6 linearly independent vectors. That's all. So that linearly independent vectors represents dimension. Okay. The n dimension space can be written as this formula. Capital psi equals this formula. Sigma over I equals 1 to n Ci psi I. Ci psi I. Ci is the expansion coefficient, usually it's a constant, and psi I is usually generally it's denoted as an operator. Just you remember that psi I is a function here. Capital psi is a total one. Capital psi is a total wave function, and small I stands for the components. Just remember this one. So we can expand this Ci psi I with respect to I, and that will give you C1 psi 1 plus C2 psi 2 plus C3 psi 3. It's a linear combination of all the wave functions. See here, linear combination. It goes up to n. So we can say this is n dimension. This psi 1, psi 2, psi 3 are called bases. Bases. Base states. Base states are called bases. And Ci, just now I said, this is expansion coefficients or sometimes distance from the origin. So psi n is the number of particles, n number of particles are there. And this psi I stands for basis. Okay, so capital psi equals Ci psi I. You remember this one, very important, often will be using it. Okay. So this is the definition for your linear operation. We started with the introduction. We said about the operation operating on a combined system is equal to operation operating on the individual system. So this is called a linear operation, linear transformation. So linear operation, and this is introduced by Paul Dirac from UK in the year 1930s. Okay, Paul Dirac. And we are going to learn a new notation now onwards. This notation, one line is there and this arrow mark is there. We call this as a ket vector. So you remember a new notation introduced by Paul Dirac, and this is called a ket vector. The element which you are going to insert, then together we call this as ket vector. See, here you have a line opposite and you have a line like this. This is called a bra vector. All bra vectors are row vectors. All ket vectors are column vectors. So they are represented in terms of column vector. So this is your bra vector. We represent in terms of row vectors. How to remember immediately? There will be a confusion whether this is a row vector or this is a column vector or this is a column vector, this is a row vector. We will have confusion. So I have a small mnemonic. See, bra vector R is there. In row vector R is there. So bra vector means row vectors. So as I said just now, any vector will be written in terms of a matrix. Correct? Any vector will be written in terms of a matrix. Can you remember? See here. So just now see, any vector. This is a vector. This is represented in terms of a matrix. See, row matrix. See, this is a column matrix. It's a vector. So any vector can be represented in terms of a matrix. Okay. So all row matrices will be written in terms of a bra vector, or column matrices will be written in terms of a ket vector. So you have ket vectors and bra vectors. Ket vectors will go with column matrices, bra vectors will go with row matrices. So remember. Now, just now I said this is a ket vector, correct? Ket vectors are column vectors. What are the components of a vector A? A1, A2, A3. Very simple. It's a column vector. A1, A2, A3. Similarly, this one will be a bra vectors. Component of a bra vector will be in terms of row vectors. So A1, A2, A3. So this is a row vector. This will be a column vector. Now I am going to combine these two. I am going to combine bra and ket. What is this vector? What is this vector? Bra vector. What is this vector? Ket vector. I am going to combine these two. When you are going to combine these two, there are two lines. To simplify these two lines, we are going to write only single line. Okay, instead of writing two lines, it will take time. So scientists have followed that single line. So this is your bra vector and this is your ket vector. Bra with ket. Bra with ket means row matrices multiplied by column matrices. We have done already. Row matrices multiplied by column matrices will give you scalar or vector. Which one? Scalar. Very good. Scalar. Can you remember? Just now we did one sum. Can you remember? See, we had we could calculate this. See here. This is your row vector. Row vector multiplied by column vector will give you scalar. So similarly, here too, row vector multiplied by a column vector. So row matrices with a matrix multiplication with a column matrix, that will give you number. That will give you a scalar. So bra vector with the ket vector will always give you a number, scalar. This is called a scalar product. Sometimes we call this as inner product. Sometimes we call this as inner product. Is it okay? Inner product is defined as bra with ket. bra with ket. Bra with ket will give you always a number. See, bra with ket. This is called the inner product. Any doubt on the slide? Now, operations. We will find out some operations. Just now we discussed about bra with ket or what we say this is inner product or a scalar product. We will get a number only. Suppose we will go for a few examples. We can go for a few examples. 1, 2, 3. This is a row vector. This is representation of row matrix. Okay, row matrix. This will be your column matrix. Okay, so I am going to have a matrix multiplication, matrix operations. So that will give me 1 multiplied by 1 plus 2 multiplied by 2 plus 3 multiplied by 3 will give me 14. Correct? Is it okay? 1 plus 4 plus 9 will give you 14. It's a number. So scalar product will give you always a number. Okay? Any doubt? Suppose if it is equal to 0, for example. What is this one? Bra vector or ket vector? What is this one? First one is bra vector. Second one is ket vector. So bra with ket. We will say always bra with ket. Bra with ket will give you number. Okay. 0 also is a number. So we will get 0 here sometimes. Answer. We will get, sometimes we will get as 1. Here we have got 14. But here we have got 1. Suppose if we are going to get result as 1, this is called a normalized vectors. Those two vectors are normalized. Suppose we are going to get a 0, those two vectors are orthogonal to each other, perpendicular to each other. So those two properties are very important, which you are going to learn now. Okay. So any doubt? So we can have either 0 as orthogonal properties, orthogonal vectors, or 1 as normalized vectors. And the second one, the earlier we did the operations as bra with ket. Now we are going to have ket with bra. Ket with bra. Ket is a column vector. Bra is a row vector. So now we are going to have a matrix multiplication. Ket with bra. Ket with bra. So you have 1 multiplied by 1. I have written like this. 1 multiplied by 2. I have written like this. 1 multiplied by 3. Yeah. Similarly, 2 multiplied by 1. I have written here. 2 multiplied by 2 I have written here, 2 multiplied by 3 I have written here. Similarly the next one, 3 multiplied by 1, 3 multiplied by 2, 3 multiplied by 3, that will give you 9. What is this one? It's a vector, it's a matrix. Earlier bra with ket, that will give me what we call this inner product, that will give me a number, scalar. Whereas ket with bra will give us vector, it's a matrix. Very, very important one. Is it okay? Very simple one. So now we have come to the next topic, which is linear independent vectors. So as I said clearly about linear independent vectors, linear combination of some vectors will be there in a set. Those vectors are linearly independent vectors. For example, ijk, they are all linearly independent vectors because one vector cannot be written in terms of another vector. Suppose we are going to write one vector in terms of another vector, linear dependent vector. So one is dependent, another one is independent. Very simple one, simple example. A set of vectors u1, u2, u3 ... is linearly independent if there exists no linear relation of the form. There is no linear relation. For example, ijk. No relation. I is different. I is in this direction. J is in some other direction. K is in some other direction. Perpendicular direction. So there exists no linear relation of its form. This is summation expansion. Can you remember? Which is equal to 0 except for the trivial one with all a1, a2, a3 are equal to 0. If it is so, we call this as linearly independent vectors. I will explain. A vector u in a vector space V is called a linear combination of vectors. For example, just take u1, u2, u3 in vector space, then u vector can be written as a1 u1 plus a2 u2 ... ai ui. I can write this as 0, u vector as 0 or vector exists. Two conditions I can apply. Suppose if I have written 0 here, if I am going to take only two components, for example, I am going to write there exists no vector I can write this as a1 u1 plus a2 u2 which is equal to 0. For example, I am going to consider only these two components which is equal to 0. Then a1 u1 equals minus a2 u2. Then u1 equals minus a2 u2 by a1. Can I write like this? u1 is one vector, u2 is another vector. I have written in terms of u1 and u2. u1 is equal to some constant multiplied by u2 vector. One vector is written in terms of another vector. So this is linearly dependent vector. u1, u2 vectors are linearly dependent vectors. Is it okay? Simple example. I repeat. See, there exists, for example, sigma ai ua equal to 0. I'm going to take only two components, a1 u1 plus a2 u2. So a1 u1 equals minus a2 u2. So you have u1 equals a2, this is a2, okay, a2 u2 by a1. a2 is a number, a1 is a number, so number multiplied by u2. So u1 is in terms of u2. u1 is in terms of u2. One vector is in terms of another vector, linearly dependent vector. So they are all dependent vectors. Suppose if it is not equal to 0, they are linearly independent vectors. Only thing is a1, a2, a3 must be equal to 0. It's trivial, non-trivial example. Okay, this is a trivial one. So where ai equals 1, 2, 3 dot dot 10 are complex numbers. Here the vectors a1, u1 cannot be written in terms of other vectors here. So one vector cannot be written in terms of other vectors. Two or more vectors are said to be linearly independent if none of them can be written as a linear combination of the others or linearly independent vectors. One vector cannot be written in terms of other vectors are called linearly independent vectors. One vector, if it is written in terms of other vectors, are called dependent vector. That's all. Okay. So these are the examples. Is it okay? It's not equal to 0, linearly independent. If it is equal to 0, linearly dependent. So now we'll go for a simple problem. Check whether the following vectors are linearly dependent or independent. So we are going to check whether these three vectors are linearly dependent or independent. Okay, so we have these two problems. We are going to solve these two problems. Very simple idea is you just take the determinant. Simple idea. Just take the determinant. If it is equal to 0, you have one answer. If it is not equal to 0, you have another answer. We'll see. If it is equal to 0, that means you have linear dependent vector. If it is not equal to 0, you will have linearly independent vectors. So you are going to take the determinant now. For the first problem, 1, 2, 3, 2, 5, 1, minus 1, 1, 4. Okay, so just take the determinant. You know how to take the determinant. So 1 multiplied by 5 multiplied by 4. So 1 multiplied by 5 multiplied by 4. 5 4s are 20. 20 minus 1. And this component you are going to take. So minus 2 and 2 4s are 8. Minus 1 multiplied by 1. Minus 1 already minus is there, so plus 1. And the last one will be minus 3, 2 plus 5. So 19 minus 18 minus 21 will give you minus 20, which is not equal to 0. So determinant value is minus 20. So the vectors 1 to minus 3, 2, 5, 1 and minus 1, 1, 4 are linearly independent vectors. They form a basis in 3 dimensions. Any doubt? Very simple one. We'll go for the next problem. Similar problem, and vectors are 1, 2, 3, 2, 3, 4, 3, 4, 5. We are going to do the same calculation. We are going to take the determinant. The answer is 0. So linearly dependent vector. Very simple one. So I have given some assignments for you. You have to, this is assignment 1. So check whether these vectors are linearly dependent or not. Okay, you just check. Okay, you can download from the internet. No worries. So you have 3 vectors. You are going to check linearly independent. You have 3 vectors. You are going to check whether it is linearly independent, and this also linearly independent. Okay, you are going to take the determinant of all the vectors. If it is equal to 0, linearly dependent. If it is not equal to 0, linearly independent. Okay, now scalar product. Scalar product. Another title we have arrived. Scalar product. Just now we discussed about the scalar product very well. Scalar product. Scalar product means inner product. We have two vectors. You are going to have a dot product. It's nothing but a scalar product. Dot product. U dot v. U is a vector and v is another vector. So u dot v, that will give you a number. So this is called a scalar product. Correct? Bra with ket. Bra with ket will give you a number. It's a scalar product. Okay? A function that multiplies two vectors to produce a scalar. It's nothing but a scalar product. Scalar products are very, very important in mathematical physics, which will be dealing in quantum mechanics very well. That will give you a result of 0 and 1. Scalar product. It's very, very important one. This will give value of 0 and 1. 0 stands for those two vectors are orthogonal to each other. 1 stands for those two vectors are normalized vectors. Easy one. Okay. So the inner product of vectors is generally defined by introducing the concept of dual space. Dual space. It's the first time we are going to deal with dual space. You have a vector. Corresponding vector, there will be a complex number. Okay, corresponding vector, there will be a complex number. You have a number, corresponding there will be a complex number. Those complex numbers live in dual space. So dual means two values. One is real, another one is a complex value. Complex value. Those two values, they live in vector space. Okay. So we always say this dagger. This is called a dagger. Dagger means in a matrix. Dagger means it's a Hermitian conjugate. Dagger represents a Hermitian conjugate. It means you are going to change the rows and columns and take the complex conjugate. You have a matrix. You are going to change the row into column and column into row and take the complex conjugate. What is the meaning of taking the complex conjugate? Suppose 5i is there. Complex conjugate of 5i is nothing but minus 5i. Minus 5i complex conjugate. What is the complex conjugate of minus 5i plus 5i? Simple. So you are going to change the row into column or column into row and take the complex conjugate. What we call this as dual. Take the transpose Hermitian conjugate. Okay. This is called a dagger. V dagger. So this is called a dagger. So this symbol is called a dagger. See, dagger. That means you are going to take the complex conjugate. Okay. For any function, usually we will take the complex conjugate. For any function. For example, we will take wave function psi. For example, we are going to take the wave function psi. The complex conjugate will be star, psi star. U is a vector. U is a function. You are going to take the complex conjugate. So it means u star. That's all. For any operator, you are going to take the complex conjugate, you will have to write in terms of a dagger. For operator, dagger. For wave function, star. Is it okay? Operator. Operator means it's a matrix. It's a matrix. In a matrix, take the complex conjugate means you are going to change the rows and columns or columns and rows and take the complex conjugate, which is nothing but your dagger. Wave function means psi will be represented in terms of psi star. That's all. Okay. So which consists of vectors having one-to-one correspond with the vector space Vn. In other words, to each vector A in the space determined by the basis ui, there corresponds a vector A dagger. So for any operator, usually we will go with only dagger in dual space. So there will be corresponding. For every vector, there will be a complex conjugate in dual space by the vector u star such that A dagger equals A star ui star, where A star is the complex conjugate of ai. Similarly, ui star is the complex conjugate of ui. Is it okay? Any doubt? So the inner product is defined as So this is a definition for your inner product, which you have already learned. A dot B is nothing but inner product, scalar product, A dot B. That will give you a scalar. So U dot B equals, and which is equal to you are going to take the complex conjugate. See here, U dot B equals U dot B, take the complex conjugate. Both are equal, which is equal to minus into plus infinity. You are going to take the complex conjugate for U star, then B d tau. The answer will be always a number, scalar. So number scalar. Okay, so scalar product is defined as U dot B, which is in terms of integral form, which is nothing but minus into plus infinity, U star B d tau. D tau stands for dx, dy, dz. As we are going to consider only three axes, 3 dimension. So d tau stands for volume element, dx, dy, dz. So you will get the answer as C, where C is a complex number or real number, scalar. The positive square root of the vector u with itself, if you are going to take the square root of u comma v, is called a norm. U comma v stands for a scalar product. If you are going to take the square root of scalar product, will give you norm or length of a vector. It means length of a vector. If you are going to take, see here, this is your scalar product. Take the root, will give you norm of a vector. Simple one. It will give you norm of a vector or length of a vector. Length of a vector for single vector is defined as these lines. So V single line, these two lines, which is equal to V1 square components. V1 square plus V2 square dot 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 Vn square. We can write sigma over I equals 1 to n Vi whole square to the power 1 by 2. So this is a norm. As I said just now, norm is nothing but root of inner product, root of scalar product. So going to square it, that will give you this. See your V equals root of V comma V, V dot B. This is another notation. This is a scalar product. V equals root of scalar product V comma V. We can write this as V squared as V dot B. Is it okay? So suppose if it is equal to 1, we call this as unit vector. The answer is, suppose if you are going to get the answer as 1, we call this as unit vector. If the norm of the vector is unity, it is called a unit vector. Those spaces in which inner product exists are called unitary vector spaces. So for example, we are going to have some operations on scalar product. So x vector is given by this, y vector is given by this, and you are going to take the transpose of x vector and multiply with the column vector. You will get answer as 8. So surely it's a number, it will be a number. X transpose multiplied by y, row vector multiplied by column vector will give you a number. Okay, so simple example. For example, u vector is here and v vector is here. U vector is given by minus 3, 4, v vector is given by 4, 3. This can be represented in terms of a picture also. Now we'll go for first u dot v. U dot v means we'll have to multiply with its own components, as I said earlier. So minus 3 multiplied by 4, 4 multiplied by 3. What is the answer? 0. U dot v equals 0 means u and v are perpendicular to each other, orthogonal vectors, perpendicular to each other. Is it okay? Now, how to represent? See, this is your v vector. What is v vector? 4, 3. 4 in the x-axis, 3 in the y-axis. See here 4. You have 4. And 3 in the y-axis. So this vector is represented in terms of a v vector. What are minus 3, 4? Minus 3 in the minus x direction. So here somewhere. And this must be your 4. So this must be minus 3, 4. This is represented in terms of a u vector. What is the answer? 0. See, both are perpendicular to each other. Both are perpendicular to each other. Is it okay? So orthonormal vectors, u vectors and v vectors are orthogonal to each other. Any doubt? You can also try for this sum as an assignment. This problem as an assignment. Okay? You just check whether they are orthogonal to or not, or otherwise you can say that what is the scalar product of u and v. You can just find out. So now we'll go for the last topic, orthogonal property, orthogonality. What is the meaning of orthogonality? Two vectors are perpendicular to each other. Very nice. And another orthogonal property is very important property is 1, 0 and 1. You must get for two scalar for two vectors when you are going to have an inner product or a scalar product, the answer should be either 0 or 1. That's very important one. 0 means orthogonal to each other. 1 means normalized. Orthogonality means perpendicular to each other. Now I am going to combine these two. Orthogonal plus normalization. What we call this as orthonormal. I am going to combine these two. So first one is called orthogonal. Second one is called normalization. I am going to combine these two. We call this as orthonormal vectors. Okay, we are going to see now. Two vectors are orthogonal if their inner product vanishes, inner product disappears, it becomes 0. Second one, these two vectors u and v are orthogonal to each other, the answer will be 0. So u dot v equals 0. Two vectors are orthogonal if the angle between them is right angle, 90 degrees. Just now we have seen a picture. The scalar product of two null vectors is 0, we know already. If the scalar product of two vectors with itself is unity, then vector is said to be normalized to unity. The vector is u is normalized to unity, the answer will be u dot v equals 1. That means u and v are normalized to each other. A set of vectors which is orthogonal to all remaining vectors of the set is called orthogonal set. Orthogonal set. If each vector of the set is further normalized, we call this as orthonormal set. So one is orthogonal set. If it is normalized, orthonormal set. A vector can be normalized by dividing by its norm. This is the norm of a vector. We have seen just now. So any vector divided by its norm of a vector this way. This is the way it is normalized. Is a normalized vector parallel to u vector. A set of vectors ui equals 1, 2, 3 dot 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 n is an orthogonal set of vectors if and only if this condition is satisfied. This condition. You have a u vector and you have another vector ui and uj. Okay, you are going to consider ui and uj. You are going to have a dot product and you are going to introduce a new letter, Roman letter del ij. This del ij stands for Kronecker delta function. Very, very important. Often will be using in quantum mechanics. Often will be using. So del ij. I and j stands for 1, 2, 3 dot 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 n. So this is called Kronecker delta function. Suppose if answer is 0. If answer is 0. What is the meaning of answer is 0? That means ui dot uj equals 0. That is ui is perpendicular to uj. They are orthogonal to each other. So 1. Suppose the answer is 1. Normalized. The condition is if I equals j, you come here, just insert I equals j. ui dot ui. Here I. Instead of j, you substitute I. So ui dot ui. Answer is 1. So if I equals j, the answer is 1. If I is not equal to j, the answer is 0. That's why I said orthogonal and normalized both are very, very important, as I said. So this condition is satisfied. So this is orthogonal. If this condition is satisfied, this is normalized. Orthonormalized. Orthogonal. Since the orthonormal vectors are linearly independent and can serve suitable basis. So they can serve as a suitable basis. So orthonormal set, orthogonal set. Just now we have seen. And this is another deviation. And we know that the expansion coefficient psi, capital psi, which is equal to Ci psi I. We know we have written in terms of a ket vectors. Ket vectors. Ket psi equals expansion coefficient Ci psi I, summation over I equals 1 to n. Okay. Now I am going to multiply on both sides by bra psi. This is your ket psi I. This is your ket psi I. I am going to multiply on both sides by bra psi I. This is your bra psi I. Psi I. So here Ci is a constant. I can pull the Ci and insert bra psi I here. Is it okay? See here, your capital psi equals Ci psi I. I am going to multiply or have the operation on both sides by bra psi I. So bra psi I with capital psi, which is equal to this, a constant. So I can keep this psi I here. So bra psi I get psi I. What is I equals? This is I and this also I. Psi I dot psi I. What is psi I dot psi I? Answer is 1. Very good. Answer is 1. Bra psi I get psi I. Answer is 1. So this answer is 1. What of this one? This is, let it be like this, psi I with psi. So your Ci is nothing but psi I capital psi. The component of Ci is therefore equal to the scalar product. This is scalar product of psi I with capital psi. It's a scalar product. Bra with psi is a scalar product. Ket with bra is a vector quantity. It's a vector quantity. Any doubt? So in such a way that we can get the expansion coefficient. The expansion coefficient is nothing but equal to scalar product of psi I with capital psi. So this is the way we can calculate the expansion coefficient. Okay, any doubt? So in this class we discussed the introduction about the linear vector space. Then second one is linear independent vectors. Can you remember? And third one is scalar product. And the last one is orthogonal vectors. So orthogonal vectors are very, very important, and we have introduced canonical delta function. The canonical delta function, if I equals j, sometimes people use n and m. If n equals m, the answer is 1. N is not equal to m, the answer is 0. So we can use either. Okay, so they are all canonical delta functions, and the answer can be either 0 or 1. 0 for orthogonal, 1 for normalized. Okay, so thank you students. We will see in the next class. Bye.